नाही ठीक आहे आपका ध्यान उधर रहता नहीं है, इंसान
So very good afternoon to all of you. Welcome back in the 5-day online FDP on flow characteristics and turbulence statistics in annual channel. So this is the 4th day, and now we are moving towards the second session. So now we have second and third session by the expert Dr. B. Ramesh, Principal, Savitha School of Engineering, Chennai. The brief introduction of today's expert is as Dr. Ramesh received his Bachelor of Engineering from Karnataka University and Masters of Engineering in Engineering Mechanics from IIT Madras. Professor Ramesh received his doctoral degree from IIT Roorkee. He has a total experience of 19 years in teaching, research and industry in various capacities and is being instrumental in driving the institute to deliver quality packed education to the students. A few awards he has won are National Doctorate Fellowship for the PhD and Best Lecturer Award from SMIT. He is responsible member for Academic Council, Board of Research, Educational Technical Units, and IRB, that is Institute Review Board. To his credit, he has 16 peer-reviewed journals published in national and international journals. His area of interest includes sedimentation studies, structural dynamics, and mechanics of structures. He teaches subjects like structural engineering, design of reinforced concrete, structural analysis to all undergraduate and postgraduate students. This exuberant knowledge makes him a stalwart. His guidance to the student is priceless. And beside Sir's busy schedule, Sir accepted our invitation for delivering the expert lecture. So I would like to thank Sir and invite Sir for delivering the session.
Thank you, Dr. Sudhanshu. And it was
Yes.
Thank you for a great introduction to me. And hope I'm audible.
Yes, sir. You are perfectly audible.
So may I know how many are here? Hello. Yeah, may I know how many are here in this meeting?
Students, sir.
Yeah, total how many are here?
Okay. If I talk about total participants, there are around 40-45 participants are there. Out of that, 18 to 20 are research scholars of ME and PhD level, and rest are some faculties from diploma and degree colleges.
Oh, thank you. I saw Dr. Ashish was here. And sir, are you there?
Ashish, sir. Yes, he is. He is there.
Sir, how are you?
I am fine.
So
It has been since a long time.
yeah.
Yes,
Very happy to see you people around.
It's good to see you. To see you through this platform.
Thank you.
That's all technology that has made it possible that we are here to and talking.
Yeah, and we should really thank Dr. Jain also for having all us.
Yeah, Dr. Ramesh, yes.
Thank you, sir. Thank you.
See,
So,
we are sitting 2,000 kilometers away from here, but we can see because of technology.
yes, sir.
Right,
Uh,
right.
yeah, thank you so much. But I saw all this schedule, and I guess almost most of the topics, many of the people are now expert, I guess, because I saw photo analysis by Dr. Jain and scouring around footing by Dr. Ashish. And I guess most of the related studies would have been covered in the previous lectures. Maybe let me see what justice I could do on my lectures. And basically this what I prefer to have is like maybe that was a very detailed work you would have seen from Dr. Ashish, and he has really done a great job in understanding the complete turbulent characteristics of footing the pier, around the pier, and that was a very interesting study. In fact, I should tell him whatever studies we made, we took from here his studies, and that was an interesting observations which he made, and that really helped us to proceed further. And also Dr. Jain also has done a lot of study on mobile beds and all the turbulent characteristics which he studied, and really it's great database for the whole scientific society. That's what I personally feel. And because of the papers which we had in WRR are really one of the best papers which people could have on turbulence. That's my personal feeling. And all these people really have put a lot of effort in understanding the turbulence. And I was also proceeding on the same lines, but in a different way. I'll tell that Dr. Jain's work and Dr. Ashish's work was like it was a bit more tougher than mine because their bed was mobile, and when you have a mobile bed there, things become very difficult to handle. And in my case, it was very rigid. I very happily I have put a rigid bed there, and I was doing the analysis because I have the control parameters was in place, and I could have a very good control over the flow that is happening over there. And that was not possible in their case. There was a lot of unknown parameters there. They didn't really know why it was happening, and with that, they try to understand. So with that, what I'll do is I'll get into the topic directly. And what as I told, I'll be focusing on my studies will be only on the rigid bed. Okay, if it was a rigid bed, and how the flow turbulence happened, and how we try to understand things with that experimental setup what we had, and that will be my primary focus on. So I'll directly get into the presentation. Shall I move on to the presentation, Dr. Sudhanshu?
Yes, yes.
Thank you.
Dr. Ramesh, it would be okay if you keep your video on.
Yeah,
So,
sure,
yeah,
sure,
sure.
sure, sure, sure. Okay, can you see this? Can you see this
Yes,
slide?
sir. Yes, sir.
Yes.
Completely visible.
Okay. So
Yes,
you
sir.
see,
Yes.
as the topic goes, I try to understand when a particle moves very closer to the bed, or when a particle moves over the bed, and how it moves, and what are the parameters that influence this motion. And we were trying to really relate the motion of the we were trying to relate the motion of the particles that are moving with the flow parameters that is making the particle to move. We are trying to understand where what was the clear link between these both, and that was the main agenda of the study which we had. And for having that, what we did was, I'll just one moment, please. Okay. A few slides were hidden, so okay. So, Bedlow
Yes, just for interrupting you, can you remove that bar which is showing
sorry.
presentation? Can you remove bottom bar? Just hide it.
Sorry, I didn't get you. Please come again.
In bottom of the slide, we are showing that information bar presenting one. So can you hide it?
It is dark.
No, sir. Actually, there is one pop-up is there. Hide option is.
Oh, pop up.
Bottom of the slide.
Oh, this one.
Yeah,
Right?
yes, that's fine.
Yes, you can make it
So it will
full.
be very
Thank you, and thanks for that. You see, in my presentation, it's having a lot of videos which are of large size. So in between the PPT may get stuck up. So I have to open that again. So kindly excuse me because of the huge image size. It's a complete image video I have put into that PPT. So in between there, it might struck. I don't know how it works. So if it got struck, kindly bear with me, right? Okay. So you see, Bedlow transport is the what happens is when you have a river, right, and you have a river bed, and in that there will be the particles which are there in the river bed will also move with the flowing water. So what is happening is, as I told, whatever the fluid parameters that is making this sediment to move, that has to be understood very clearly. Then only we can understand this Bedlow transport. And because of this complete random nature, it is one of the very difficult problem to study. So that makes the problem still vibrant, because what this is being studied by a lot of people previously, and Einstein have worked on that, and still it is not saturated. It means to say that it is a very tough problem, and people are trying to address it from all sides. And this is one way we try to understand the problem. And you may think, what is the need for understanding this Bedlow transport? Because it has a tremendous practical applications. If you see, a lot of bridges are there. And many of the bridges, maybe from Dr. Ashish's presentation, you would have seen that the scouring is a very, very important problem which bridges face. And it is become all the bridges can become a big disaster if it was not addressed properly. And some of the examples which you could see here is these bridges have just failed just because of scouring action. And we may think that the bridges, many of the bridges failed because of the structural failure. But practically, if you see, if you see the statistics of the total bridge failures around the world, nearly 40 to 60% of the bridges have failed just because of this scouring problem. It was not a structural failure. And you can see here in the figure, which we have in Bihar, and in that bridge, the bridge is structurally safe. It has failed only because of the scouring happened. So we need to really address, and most of the bridges what we have here in India at present was constructed long back. And the upstream characteristics of the flow that has changed tremendously because of the whatever occupancy there in the upstream side of the bridge, or so as the downstream side, that has tremendously changed. And because of this, what happened, because of the change in the flow parameters, the complete bridge previously which was safe, now it has become unsafe. So we need to really understand what flow makes this soil to move out, and how to arrest this scouring. This is one of the examples which needs a clear understanding about the Bedlow transport. So like this, you have a lot of applications where this understanding is very, very essential. And if you see, if you go to literature, as I told you, you have tremendous work. people have done interesting and lots of work is available in bed load transport. And if you see, people have, as I told, they have approached in different ways. And it will be very interesting to see that what were the outcomes that they have achieved through their studies. And these are a few people who really impressed me on the bed load transport. These people have really worked very hard, and these people have really gave an idea that bed load transport study is very much possible. And with all the tremendous achievements or innovations which we have at present, I think we should get to know much more things in detail. With all you people around who are doing a lot of research in hydraulics, maybe the days are not too far so that we will understand bed load transport in much more better way. And if you see this, as I told, the bed load transport directly depends upon the flow that is happening above the bed. And this flow that is happening above the bed, that decides whether the bed is considered as a rough or a smooth or a transitional. We can categorize that into three categories mainly: a smooth bed, or a rough bed, or a transitionally rough bed. And you can see a lot of literature, people have found that it is a hydraulically smooth bed they had, and based on that they had some studies. And people also had a lot of studies on rough beds. And all I'm talking is about the rigid beds, right? And in between, there is a transitional zone where because of the flow characteristics, the bed cannot be considered as smooth, or also it cannot be considered as a rough bed. So we call that it is a transitionally rough bed. And in this transitionally rough bed, not many people have done studies on that. So the complete literature tells us that this understanding on a transitionally rough bed can also give us more insights to this sediment transport that is happening there. So what we thought was, based on all our understanding in the based on our study in the literature, we found that we can work on transitionally rough bed. And first, we categorized our objectives into two things. We see our bed is now we should clearly understand that our bed was rigid, right? Our bed was rigid, and on that rigid bed, we have the flow. Say I have a bed, river bed there, and I have the flow that is happening there. So when the flow is happening on that bed, it also tries to move these sediments away. But in my case, what is that I have is the bed cannot move; it is rigid, right? So I maintain the flow parameters in the top so that the bed will come under the category of a transitionally rough bed. So we did two studies there. One was I made the flow to happen straight. So we had a flume there, and we had the flow, and that flow was happening in a straight line, right? When this flow was happening, then how the flow was varying when it is a transitionally rough category, that was studied. Then what we did was I dropped some of the sediments, motion of the sediments in a rigid bed. When it was dropped there, this sediments was also moving on the top of the bed, right? When it was moving, how it is moving, and what parameter of this flow that is trying to move this. That's what my main objective was, to understand what was the link between that. So for that, we had a straight flow and a skewed flow. Skewed flow in the sense I have the flow, there's a disturbance in between, and you can very well take that as a pier. And you have a pier in between flow. That when an obstruction is happening there, this flow comes and it takes diversion and goes away. When there is a deviation, skewed flow happens there, what happens to the turbulence? And when this turbulence is happening like this, what happens to the particles which is moving below? What is the link between that? Okay, that was a clear objective which we had in our mind when we started this work, and for doing that study. So what we did was we had a flume, because this is one of the very, very interesting equipment which we have in hydraulics with a flume. If we have a good flume, we can do a lot of studies in hydraulics, and we all were very lucky to work in IIT Roorkee because we had a number of flumes there. Whatever the size of the flume you ask for, you will have it there. And there were many flumes were there, and we all were working in different flumes there. And this was the flume in which we were working on. Like you see, that length of the flume was 30 meter, and if you see the width, that was 1 meter, and the depth was 0.6 meters, right? And that was the flume standard we had there. And in the side for observing what is happening, and you can see that in the sides there are some glass walls are there, because these glass walls are very, very important for the study which we had, which we are going to see now, because we'll see visually what is happening there is what we saw through a camera. That was the our stadium. So these side walls were on glass, and this was the flume which we had, and the working section was 3 meter long, and it was located at 12 meters downstream of the flume entrance. You see, these all measurements are very, very important. When you see that at the place where you are doing a working section, how long it should be, how it is decided, all that are very, very important, because otherwise you will not have a good flow, steady flow, whatever you want to maintain. If you want to maintain, that should be of this much length away. Otherwise, it will get disturbed by the inlet disturbances, so as in the outlet. So this was a very long flume. In the 30 meters, you can see here, we had our working section 12 meters away from the entrance. And after that also, you have a lot of distance, so that the flow will not be disturbed in the working section there. And this was the flume we had, and then to measure the discharge, how much of water is coming into the flume, and that was studied using ultrasonic flow meter. And this ultrasonic flow meter was fixed in the inlet pipe, which was taking the water into the flume, and we have fixed the ultrasonic flow meter, and that measures how much of discharge is passing through a pipe. You see, it's another interesting equipment which was commonly used in a field of hydraulics. And same, and the next equipment is the standard equipment which we use, that is a sharp crested weir that we had in the downstream side of the flume, and that also was used to measure how much of discharge is passing. But anyway, these two were comparable, this ultrasonic flow meter reading and the sharp crested weir. Both readings were used for a comparison. And if you see, this was an interesting equipment, and I guess in the previous session I saw a topic on how to measure the velocities using an acoustic Doppler velocity meter. Maybe I guess it was Sudhanshu. I don't remember. Sorry if I was wrong. So that same ADV was used to measure. Now you have a lot of advanced equipments, right? And this, you should understand that this equipment was we used maybe some 14 years back. Yeah, 13, 14 years back, we were using that. And at that time, it was really of, it was giving unbelievable data, I'll tell you. Right? Now it is quite common, but at that time, you see the rate of with what it is giving data was tremendous, and we were having data with 50 hits. That was really a good volume of data to understand. But maybe when you are when you're talking about turbulence, even this looks less, right? But it is large. But if you want to really look into turbulence, I guess you should need some more and more data, I guess. But what we have done here is, like, we used a 16 megahertz micro ADV, and the sampling rate was 30 hertz. 30 hertz was a good number, quite good number. You see, and with this 30 hertz, we took a reading at any point of time. If you want to take a reading, we were taking it for 4 minutes. So if you see, I take a reading for 4 minutes at one single point, you will get around close to 7,200 data. 7,200 data we get at a single point. Okay, so like that, you can take this data at any point. The idea is all these 7,200 data will be taken, and there will be noise will be there will be errors will be there, all that we can filter it out, and after filtering out, we can take a good data, which we feel that it is one of the best data we have. And with that data, we can narrow in whatever parameters you want to understand, that can be done. So as the figure clearly indicates, that you can see here. So this was, we used filters, as I told, that there will be a lot of noise and other things will be there. So all that will be removed by this SNR and COR filters. And then this was the graph where we have the instantaneous velocity, right? After removing that instantaneous velocity, if you plot it, you get a beautiful bell curve like this, right? And this was having a clear distribution. All these velocity data which we get, we have a clear distribution over there. And so as I told, we had a flume for this flow. Then we had ADV that was used to measure the flow parameters that is happening. Then we had a very, very important high-speed imaging system. So as I told, the flow parameters were measured by that. And when a sediment motion is happening, that sediment motion was captured using this high-speed imaging system. So this high-speed imaging system was very, very powerful, and always keep in your mind that was used 13 years back. 13? Yeah, 13 years back, right? And at that time, we had a high-speed camera which can capture more frames per second, but for having a good resolution of 640 by 480 resolution, we were using 210 FPS. That is frames per second. It means that within 1 second, it can take 210 photographs. And that was the speed of the camera. And if you go resolution, if it was not an issue, then you can go with 2000, 3000 frames per second also. So the cost, but we want resolution also good. So we thought that, okay, 210 frames per second was reasonably good enough to capture that. And then we had a digital frame grabber and a high-speed data logging system that was used to capture all these required data. You see, and these two are the softwares which were used to understand this study. You see, that was image was captured using the high-speed camera, and after that it was processed using the Image Pro Plus software. And you see, why I say that it is very, very high speed is important means, maybe I can show you a video. You see, just see this video so that you will understand how fast things are happening around a pier. And okay, can you see that? And I don't know, that's the buffering is happening there. And you see this complete flow that is happening in the upstream side of the pier. This is the video we have. And you see the flow comes, it hits the pier, then it goes down, take the sand with that, so all the sediments with that, and take it to the downstream. And if you see that, and maybe it's buffering there. If you see the real video, you could see that it's tremendous. It is like a miniature robots working there tirelessly to remove the soil. That's how it works. Continuously it happens, right? And so this is an important video. I consider this is an important video. Why? Because you see, this will clearly make you to visualize the need for this study on turbulence, the relation between the turbulence and the sediment. And you can see all these flow parameters, that is the coming down, taking the soil, coming down, taking the soil. So the parameter with what, the flow parameters with what it is, the flow is coming, and how it is hitting that sediment, and how the sediment is moving, when it starts moving, why it starts moving, and how to, if we understand this motion clearly, then we can take, we can do something so that the sediment will not move. Okay, When you know how the motion happens, then you can find a way to arrest that. Right now, the problem is we did not know because it was a clear understanding was not there. And all these were laboratory experiments with controlled parameters and river bed, everything is on controlled parameters, but that is not the case when you go for a practical field. So much more things are required in this understanding. And okay. So as I told, now you know what was the experimental setup we had and why we need to do that. And with this experimental setup, as I told, the two set of readings were two groups were studied. And the first group was it was a straight flow. And you can see here in a straight flow, the flow is happening straight. And in that, what were the turbulent characteristics that was studied using an ADV. And I dropped sediment there. And when you drop a sediment there, how the sediment moves there, right? And that was studied and both was linked. And that was the first group. And second group, okay, maybe when you go to that experiments, you will understand things better. Right, and this was the turbulence measuring equipment which I was talking about. It is an aquatic Doppler velocity meter, which we used, and you can see here that was placed here, and and the flow was measured. And as I told you, this ADV measures only velocity in 3 dimensions, right? A pitot tube which measures the velocity in one single direction, and this will measure in 3 direction, U, V, and W. And that is an instantaneous velocity it measures. As I told you, it was measured for 4 minutes, so it gets you 7,200 data. And with that data, flow velocities will be measured, and after that, it's all post-processing. So ADV gives you only the velocity in the 3 directions. Then from that, we can find out turbulent intensity, turbulent kinetic energy, and Reynolds stresses, skewness factor, diffusion factor, flatness factor, these turbulence and bursting events. Maybe in all your previous lectures, you are now an expert on that. And you all clearly know that how to find out the turbulent intensities, right? When you have an average velocity and what is the instantaneous spike in that, that will be considered and that will be taken as an for finding out the turbulent intensities. Maybe you people know that, so we'll directly get into that. So these were the flow parameters. You see, basically it is an experimental study which I am trying to explain you. So you should all clearly understand, you see, what was our objective, and for reaching that objective, why we are designing. These are all meticulously designed so that our study will be very clear. So whenever you do a study, these all control parameters should be very, very strictly maintained. Because if we deviate a bit, then we really do not know why it is happening. Because already it is all in a random nature there. So whatever things which you can control, you should control it perfectly. There should not be any if and buts there. So when you have a clear control over there, at least we can understand what is happening in the other side. Right, and these were the two flow parameters for flow depth, which we were using there. One was we were having a flow depth of 15 centimeters, and other one was 20 centimeters. And the flows, water surface slope was measured, and discharge was also measured using the ultrasonic flow meter or a sharp tested weir. And the average velocity of the flow was also measured. You see, that also can be got from the ADV data. In addition to that, we have other methods also to find out that. And from that, we can find out what was the Reynolds number of the flow, and so as the Froude number of. And we know how to group this bed into 3 categories. So it's hydraulically smooth bed, transitionally rough bed, and completely rough bed. That that can be done with this parameter. With the Nizuan has given a clear way to distinguish these classify these beds, right? And these beds can be, and you all should understand that it is not just the surface roughness we talk about. When we say that it is hydraulically smooth, means I'm talking it is hydraulically smooth. It is not just physically it is smooth. The flow that is happening above that bed, that decides whether this flow is hydraulically smooth bed or a rough bed, right? So it is not just the roughness of that bed. So based on that, we had this classification. And then we had we measured the instantaneous velocity for the two flow depths which we had. And we see that nearly some 15 to 20 to 30 points we have measured across the flow depth. And it was, we have found out really how the velocity distribution has happened. And you can see for the two different depths, that was we have found out the average velocities here. And after this velocities, what we had is we have found out, and you see, we based on this fluid flow, based on this flow characteristics, we can decide that it is smooth or rough. And you can see that the Prandtl equation was used for the smooth bed, and for the rough bed, we had the Nicorat's equation. And transitionally rough bed, yes, Raux has given an equation for that. And what we did was with that equation, we have simulated the values, and you can see the two lines there. And our data was clearly falling in between the smooth and the rough. So it was categorized as a transitionally rough bed, and all the data points also clearly goes through the equation given by the route also, right? And this clearly shows that flow that was happening is transitionally rough. And in this transitional rough, as I told, when you have a smooth bed, what will be the value? And it's a rough bed, we have a value. And also transitionally rough bed, we have another value. And these all were the vertical distributions of the turbulent intensities. And I guess more details on the equations are not required, because the previous lectures, you would have seen enough of that, how these turbulent intensities are computed from the instantaneous flow velocity. So that can be directly, that same equations what they would have discussed in the previous lectures were used to find out these turbulent intensities. And the turbulent intensities also we had in all these three directions, because we had the flow in these three directions. And from that, we have found out what was the vertical distribution of the turbulent kinetic energy also. That was also post-processed from this turbulent intensities. And you can see the equation which was used to compute this turbulent kinetic energy. And the vertical distribution of the Reynolds stresses that was computed. You see, this is all across the flow depth, and it was made down dimensional by Z by H. And you can see in the coordinates what is shown there in the diagram. And you can see that these are the vertical distribution of the Reynolds stresses. And the complete fluctuations of the flow, that was also drawn. All these, because I told you we have 7,200 data points there, all these were drawn, and we can see that it follows a clear bell-shaped curve. And it clearly follows one distribution, all these flow. And it also could be seen by the previous researchers what they have found. It is also synonymous to that what they have done. And then we have found out from the turbulent intensities and the kinematic and kinetic energy. Then we have found out the vertical distribution of the skewness factor. And skewness, it really tells about the distribution shift in that distribution, whether it is a negative skewness or positive skewness, because all these skewness and kurtosis values plays a vital role in this understanding of the quadrant analysis also, because these values and the quadrant analysis value tells us about when the particle will get lifted and when it moves. So that was the understanding which people were trying to get from this all analysis. So we had a skewness factor, and you can see that the variation, how it changes when it comes closer to the bed. And you can see here, which was the skewness factor, which was very high when it was closer to the bed, and it was moving when it was moving to the middle of the flow, it was less, and again, it was getting more negatively skewed. And when you go to that top surface, you can see that it is getting positively skewed. And again, this is the diffusion factor, and so as the flatness factor was also found out, and it was closely coming close to that 3 value, and it was all matching with this previous work that was done. And this was the bursting event analysis, which was done using the quadrant analysis. And this all, maybe in that Dr. James's lecture, I guess, you would have now understood what is this I'm talking about. And we have outward interactions, ejections, inward, because all these fluctuations in the flow that were divided into 4 quadrants, right? And the fluctuations both are positive, then it comes into first, and if it was a negative and positive, it goes to the second, so on. So when it is distributed, when all these distributions were taken, and this was plotted, and you can see the variation when the close to the bed, because when you are going to very close to the bed, how it was happening, and this is what we were trying to understand in the sediment motion. These all were the flow parameters that was happening in the flow. Straight flow is there. As I told, it's all post-processing. It was only the ADV gave an instantaneous velocity, and from these V values, U, V, and W values, we could do all this post-processing. And because of that much volume of data, this much post-processing is very much possible nowadays. So with this, we have got what was the complete flow characteristics. Now you clearly know what is what is the nature of the flow that is happening, right? When flow is happening there, how it happens. We had a very detailed understanding of the flow that is happening. Now what we did was, when the flow is all clearly known, now we have dropped into the sediments into that. Then when we drop some sediments into that, how this flow is taking away the sediment was our next study. So for this study, what we had was like, we had a setup like this, and you can clearly see that we have a flume, and in that flume, as I told you, that in the side of the flume, we had a glass wall, and in this glass wall, in the side of that, we have placed the camera. And this was a high-speed imaging camera, so that was capturing the flow that is happening. So when that rectangle, you could see rectangle, you could see that this was the view area of the camera there. And in the upstream side, you see a micro ADV, which that has measured the flow in this direction. And this was the, area where we are focusing on for the capturing of these images. And after capturing the images, it was directly connected to the data logger, and so as to the computer, so that the post processing could be done there. And this was the setup which we had for this to understand the sediment transport, right? So like, and if you see the sediment transport, yeah, it can move, and you should understand, never forget that I'm talking about only rigid bed, right? And there is no, it's not a mobile bed. So there's no movement of the bed there. So I have made it very rigid to understand, because that will not disturb my sediment motion. The sediment motion is just purely happening because of the flow parameters that is making that sediment to move. That was we are trying to understand. And when you see that these sediments, when it is moving, that will not always move in same way. And you see, there can be, and in the majority of that will move in this, as is shown in the image, it jumps, saltation. We call it as a saltation, right? This saltation, this sediment keeps on moving there. It keeps on jumping, right? It jumps and it keeps on moving. And this is what we say, it is a saltation. And if you see other one, that's the sediments will be just rolling, right? It will not like, it will not saltate, it will not get lifted from that bed. But even in rotation, there will be a slight lift, but it is negligible when you compare to that of saltation. Saltation, it will have a huge jump, right? So this is all in rolling. And if you see these particles that is moving in rolling terrain, is it all again, if it is a saltation or rolling, that depends upon the flow that is happening. The flow decides whether the particle should saltate or move. And again, also, obviously, the characteristics of the sediments also plays a vital role in this movement and the saltation or rolling. And there is another regime that was also found, observed there, that was sliding, right? It was not saltating, it was neither saltating nor rolling, it was just sliding. And this is very, very, very negligible numbers were doing this. And it all, again, the shape and size also matters, whether it slides or saltates. But we observed some of that, so we thought of reporting that also. So we had a, sliding regime also. These three were the ways in which these particles were moving over a rigid bed. But here in our primary focus will be on rolling motion and saltation motion, and we'll not talk about sliding because it was very, very less. And you see, usually as we do in the hydraulic studies, we do a dimension analysis to understand the relation between the parameters, the functional dependence of particle velocity, the velocity with what the particle moves, that can be related with the fluid flow and the sediment bed parameters. So what we do is we did as a dimension analysis to understand what is the dependence, and you can see very well here that that is a function of dimensional particle velocity, where omega is the fall velocity, sediment diameter, and density of the sediment, density of water, average water depth, friction velocity, use charge, and Ks is the roughness, and the kinematic viscosity mu of the water. All these parameters really decides this dependence of the sediment on the sediment motion on the flow. Okay, so flow parameters are very well understood. Now, as I told, we are getting into that imaging, how to capture this image motion and relate it to the flow parameter. So here, as you have seen from the previous dimension analysis, the shape and size of the sediments and characteristics of sediment are very, very important in this study. So here, what we did was to understand the sediment characteristics. We used another camera. We say that it was a high resolution camera, and it was really, really having a great resolution, so that even the finer surface observations could be made using that camera. So we had whatever, because why we had that, there's another question. You see, we had to make a study, and if I say that the diameter of the particle, if I'm using is 1 mm, say 2 mm, 3 mm, something like that, I have to make sure that it is of all or of 3 mm. So if I take it in a random, in a group of sediments that is passing through the sieve analysis and take, there are chances that the sizes may be of different one. So to have a uniformity in the sizes which we have used for the study, we did particle characteristics were studied using a particle shape analysis. So whenever we want to drop a sediment there, we take it and put into this below this camera, and we observe that carefully. And if that sediment passes our test, and we would have decided what should be the characteristics of the sediment. So you can see here this way the different sizes, the different sediments that was used for our study. And you can see here we used a diameter of 7.15 mm. That was a bigger size which we used. And we had 4.05 mm, 1.7 mm. And also these all were the regular sediments which is available with the regular specific gravity. You can see here the specific gravity was 2.65, which we use in our regular studies. And one more we did was some weeds, which are the naturally available weeds on that tree. And that was also used, and it's said, and you can see that its specific gravity was 1.159. And it was nearly less than half of that sediment specific gravity which a regular sediment has, because we are also trying to understand what relation it has in that moment. So that was also taken. And you must be wondering where you get all these sediment with this wonderful colors. These are all not natural colors. These are all like we took the sediment and it was coated with paint, right? And we painted this sediment because again it's to have a uniform roughness. That was one thing. And other point was like to identification in that flow. Is it this camera has to capture, and I should really understand which particle is what I'm tracking. So for that we had different colors also there. And I understand there's a limitation because this it's not natural, it's not an exact replication of the natural sediment there. So this will be, this sediment is moving. Sorry, just a moment.
Sir, you are muted, sir.
So your mic is muted, voice is not coming, sir.
Sir, voice is not coming.
Right. Okay. Thank you. Can you hear me now?
Yes, sir. Yes, sir. Yes,
okay,
sir.
okay.
Yes, sir.
So, thank you for the feedback, but please keep talking to me so that I'll also understand whether I'm really talking to you people or I have my net got disconnected or something. So please keep talking to me and feel free to comment anything, whatever I talk in between. If it was a one-way communication also, I don't think it will be that great. So please feel free to talk in between. You ask me, and rightly pointed out my mic was muted. So that please give me some feedback so that I understand that my point is communicated.
Sure,
properly.
sure. Thank you so much, sir. Sure, sir.
Thank you. So this was the particle shape descriptions which we have got from this image analysis. As I told, this high speed image, I mean high resolution camera, that was really helpful to find out exactly. So we have fixed some parameters. These were the shape descriptions of our particles which we were using. So whatever particle I used for the study, whatever the results that was reported, that all have passed through this, right? If it passes through this all limitations, then only that was this characteristics, then only it was used for our study, right? So that was the critical velocity of the particle. That can also be found out using different ways out there to find out the critical velocity of the particles. But here we use the Nowak and Allouris method, which was more closer to the study which we had. So their equation were used to find out the critical velocity of the particle, right? So the critical velocity of that was found out, and now you see it is a very, very important table which we had. So here this table clearly tells you what were the different particle sizes we had, what were the particle density, and what were the particle fall velocity, right? And what was the flow depth we have used, and what was the shear velocity used here, what was the critical shear velocity. Shear velocity and critical shear velocity, very, very important parameters when you go for a study of the mobile beds there. And mean flow velocity, then we have Shields number, the very, very famous and important number, which when we go for a bed load transport. And based on these parameters, because of all these computations and equations what we had, and we have categorized our flow in such a way that we have the sediments that are rolling as well as saltation, because that was our focus on. We want the sediment to saltate. I want the sediments to jump, and we also want the sediments to roll, right? So how do we decide that? It all depends upon the flow which you are giving. So I give a flow, I set a parameters in such a way that my sediments will move, and it will move in saltation as well as rolling. Okay, so that were the two conditions we had there. And then this was the complete experimental setup which we had. You can see that, and interestingly, almost all the image capturing was done in the midnight, because there was no external light issues there. So we had a clear focus on that in the midnight. Close to 10 or 11, we used to start these experiments. And this was, you see, we had a camera there, and it was captured. And in the box, you could see that what was the view of the camera we had there, right? We had a rigid bed there, and the sediments. Can you see that? I guess it might be very small.
Yes, sir. Yes.
Okay.
Yes.
So there were a
Yes, sir. Yes, sir.
very, thank you. So that was a very, very smaller particles that was moving along the bed, right? So that's what it was. We were having. This was the experimental setup. We have. I'll show you an image, but now now a warning signal comes. What? I'm going to play a high resolution, high speed imaging video. So PPT may get stuck. So kindly bear with me. If it gets stuck, hereafter I'll play that as a video. I'll try with this one video in PPT. If it works, we'll continue with that. If not, I'll play it separately. Okay. So we'll see how it moves. Does it move? Yes. Can you see that? It gets stuck or it is moving. Can you see the motion?
Lagging is lagging.
Lagging is
Video is
there.
lagging.
I'm sorry for that. Yeah,
Yes, sir. Yes, sir. We can see.
I could see. I guess there was, yeah, there is a lagging. It is so unfortunate. If it was a live lecture, then you would have.
Sir, I think rolling is there. Rolling is
There.
happening.
Exactly, perfect. It is all rolling is what is happening, right? Maybe I can show you some other videos at some other time. And it was very, very interesting to see that. I see the, rolling is happening. Usually we we cannot see that in our naked eye. With the velocity with what this is moving, you cannot see that really. It moves just like that. Within a few seconds, within a second it will pass all that. So, but these images were slowed down so that we could see that. So let me check. I think you could see some of that, right? Right. Okay.
Yes, sir.
So
Yes, sir.
let me see if I run it in a line. Where is that? It is a round compress, saltating, rolling, sediment transport, sliding. Okay, let me show this. If it is okay. Will it work? Let me check. Can you see some of
Yes, sir.
this?
Now, yes, yes.
What is
Yes, sir.
happening?
Perfectly.
What is happening?
Sliding, sir. It is
Very good.
sliding, sir. It is sliding.
Sliding, sir, sliding.
Very good. This is what I was telling you. These are very limited particles were moving in this regime, right? Not all particles were moving, but this was not considered for our study. It was just to show you that there is also a possible way of movement there. So let me see whether I could show you rolling also through this. That was like, this was like, okay. This is sliding and what is happening?
Rolling, sir. It is rolling, sir.
Can you observe that clearly?
Rolling, sir.
Yes,
Rolling, sir.
sir.
Yes, sir.
Yes, sir.
Okay. And mostly these were all rolling. As I told you, you can never see that by naked eye. It is only because of the high-speed camera we could see this one. And maybe I'll show you one image on saltation. Sliding, rolling, and saltation. We have. What is this? Temporary here. You see, this was a general sediment motion that has happened actually. There's a it is all moving. I think it's buffering. Can you see that? Maybe
Yes, sir.
it's not visually that appealing, but anyway, okay.
Yes, sir.
Okay. Right. Now, this was as a Stalling told, that is all about a rolling regime, and then we have a rolling. And what we had was there were different particle sizes that was rolling. Whether this will roll. Okay, hope you can see that, right? So in this rolling, what we did was what processing we did. So in this, you see, this is all complete image particle tracking technique is what we use. And here we had a color image there to handle things better. We converted to a grayscale image. Then we do a lot of image processing application like a logical subtraction. Like there was a frame, as I told you, we had like 210 frames there. One frame was there and another frame was there. This was captured between microseconds. It was captured. So this was subtracted from this. So what happened is the background information was removed and it was only the particle will be visible. So the tracking becomes easier. These are all some of the image processing strategies, which techniques which people use to understand or get the required details from that images. And a complete particle in the bottommost image, you could see that how the particle has traveled. And you can see a lot of dots there. These dots all tell you the location of this particle. And what we did was we found out the velocity using these images. And you see, I know what is the you know what is the time taken between one point to another point, and you know what was the distance traveled between these 2 points. So based on that, I can find out easily the velocity, meters per second, how much of distance it has traveled in that time. So that was that which was used to find out with the velocity with what the sediments are moving, right? And the complete motion characteristics of the particles were found out using all these imaging techniques. It is all basic. Imaging is not a big deal there because it's all about, it tells you the some mathematical calculations and very, very simple. You see, it all directly gives you, it's all a distance and time, nothing special there. So if you know how much time it takes to travel from one point to other, that's it. Nothing more you have. But the only thing is, it goes, it's all two-dimensional, right? It's not a three-dimensional one. So in X direction and Y directions, we can find out. And if it moves up, then there will be some resolution of forces that could be done, and we can find out that also. So yes, with all that details, we got the kinematic characteristics, how the particles are moving in rolling. When the particles were moving, how it was moving, and what were the velocity with what it was moving, and which particle was moving with a higher velocity, and which was having a critical shear velocity, in what velocity it was moving in the X direction, Y direction. So that understanding is what we are really looking forward, and that we really got that. You see, and we really know now with in u velocity what was the, I mean, velocity with what it is moving in u direction, and also in the y direction. That can be found out, and all these complete particle velocities were fitted into again a diagram. It was not so beautiful as we had in that. Flow, because in the using the ADV we got a flow, and we got a very beautiful distribution there. But here it was not that beautiful, but we got some relation. There was a spike and it was moving there, but it is quite natural. It is nothing special over here. So this is what we got from the velocity distributions, what we got from that particle velocity. And all these particle velocity were also done with the kinematic characteristics of the particle were also found out using that fluctuations in the velocity. As I told, we had an average velocity with what the particle is moving, and at each and every point, how the velocity fluctuates in the direction. That was also used to find out these things. And this was the one in saltation. Let me check whether it saltates. Yes, it beautifully saltates in my system, but I don't know whether, yes, it is buffering in your system, I guess. But can you see that it is saltating? There's a lot of buffering there.
Yes, a little, sir.
Yeah, a little bit you can see. Sorry for that because of the I mean, internet issues. I guess there are buffering, and also these are all very high resolution images. So I don't think you could. But I have beautiful images. Maybe if we have some other opportunity, I can show you so that you can see this one. Okay, this was saltating. So previous analysis complete. What we made was on rolling, and now we had in saltation, and you could see that. The size of the equipment, size of the particles which I was using. You see, you should, I don't know how many of you noticed that. And in my rolling regime, it was a 7.15 mm was the size, and the density was like 2.65, right? And the 4.05, both sizes were rolling, right? It was all rolling. And when we went with a specific gravity, that was half of the specific gravity of the sediment, it was saltating. And this was that weed, and that was saltating. So you should understand that specific gravity that also decides. And this is a very small size, 1.7 mm. So that was also saltating. So diameter matters. So as the specific gravity of the sediment also decides whether this particle should saltate or roll. Okay, these were some of the tracks that was traced by the particles, you see, and it has beautifully saltated, right? There's a beautiful saltation there. And there was a huge jump by some of the particle. If you ask me why it is jumping, I don't know. Because it really, there are some particles that were jumping, maybe that angle of hit with what it is, it matters there, but I really did not, I could not find out. It all depends by the mechanics of that. We could understand maybe with the angle with what it is hitting down, that gets bounced much higher, or the bed parameters. Really, that was only very few particles were doing that. Rest of that were following the same saltation cycles which are shown in the above figures. Right, and that was that we have got, and this saltation at each and every point, there were velocities were measured, instantaneous velocities of the particles were measured, and these all velocities were averaged, and we got an average plot, and the average velocity is also shown there. See, it's a beautiful plot. We know that it is easy. You know the physics behind that. We understand. We know that it clearly you will get a plot like this only, but it is quantified here using these cameras, right? You see, when a particle, you can see here, the particle comes, it hits down, then there is a sudden jerk, and you could see that it's a seesaw like motion. It comes, it gradually comes, hits, then sudden rise, then it gradually comes, hits, like that it goes, and it's only a part of that. Images is what we have put here. So one in the right side was the special particle, which it was saltating very huge. So that was also just for to show we have done that also. And the kinematics of the complete particles in the saltation regime was also found out. You can see that it was all the values which we have found out in that rolling regime was also we found out here also. So all these velocities, you see, it's all very finer data, which otherwise we don't get, right? This is all the particle which moves inside the water. We really do not know how it moves because of all these high-speed imaging techniques and latest developments. These all things are possible. What we cannot see, a camera can see and tell us, so that we could capture all these images there. And a similar analysis actually as we did for the saltation regime, rolling regime, it was done for the saltation also. Here you can see that it was more, there it was more distributed in the saltation, but here it was more focused in the center. Peak was very high here in the saltation. And again, the fluctuation analysis of the kinematic analysis of the particle was also done here. And the complete saltation height was measured. Each and with what when it is saltating from the bed, how much height it was going, right? That was measured by imaging technique, and that was when it was compared with the previously done. People have done previously similar techniques was done for a rough bed and a smooth bed, and we can clearly see that this transitionally rough bed falls in between that two. And this was the result of this saltation. And we had you see, there was a bed was there, and that was a complete saltation was there. The height of that was measured, and the length with what the saltation happening, that was also measured, and that was also reported and compared. And you see, there are last 2 points are there. Any guess why it is much away from the previous values? Any guess? Okay, so we used a different specific gravity things also that was used. So that is the reason. The remaining all were natural sediments there, which was compared, and this was the beads that was having this one. And these were the average particle velocities that we have reported, and all these data, how it was computed, it's all available in our publication in JHR. If you find that it's a transitionally rough bed, and that has all the complete analysis of these values, it tells you how it was computed and how we got this. All that was that's clearly explained over there in that paper, right? So with all these database,
Excuse me, sir.
Sorry.
So at which height we considered the saltation?
Sorry.
The particles in saltation. At which height we consider the particles in saltation? While in suspended
You see, suspended particles are entirely different. You see, suspended particles means it loses complete contact from the bed. It will be always in the flow. This saltation
at which height from bed?
Sorry.
The
Sorry.
saltation particles at which height from bed?
It not from the bed.
Saltation particles.
Sorry, I couldn't get you clearly. Somebody can help?
Yeah, Dr. Ramesh. Dr. Ramesh.
Yes, sir.
Hello, can you hear me?
Yeah.
Dr. Ramesh.
Please go ahead.
He wants the trajectory height. What is the trajectory height from the bed?
Trajectory height he wants to know. Okay.
Yeah.
Okay. That saltation length and you see the height of that we have made it. Thank you, sir. And you see we made it dimensionless. That's what we have. You can see here the saltation height was divided by the diameter of the particle. So usually,
suppose any side of the particle is there, dm, then can you say in terms of mm? Suppose 4 mm particle is there. What was the length of the trajectory and what was the height of the trajectory which you have observed? That's what the participant is asking, I think.
Okay. Yeah, and that's what I'm trying to explain using this diagram. You can see here this saltation height 0 to 1. It says, you see, 1 means all these particles is having, and you can see here in the axis you have like a saltation height divided by the diameter. And if it is 1, it directly shows that the saltation height was equal to the diameter of the particle. And if it was 7 mm and the saltation was also having a 7 mm height, right? And in some cases, we had 1.5 to even 1.8 mm diameter of the particle. If as the diameter, you could see that it was, for example, if it was 6 mm, then the saltation height was say around 7 mm, 8 mm, 6 mm, something like that. And that was the height we had. And if you see the saltation length, and that also.
So is your question is answered? Just to participants, over to participants. Is your question answered, please?
No.
No, just continue, sir.
Okay, no issues. Easy. I'll do one thing. I'll open my tab and I'll draw a diagram and show you maybe after this.
Okay, sir.
Okay. So that was about the saltation height, and what we had was like this average particle velocities were all found out, and we tried to fit into a formula with all the observations what we had. we try to find out with the flow parameters. As I told, it was just a moment, please. Sorry again. So you see, with all the parameters, flow parameters and the sediment parameters, what we have got, we try to fit into the formula, and we have arrived one formula, which was like the previous researchers also tried to find out a relation between all these flow parameters and the sediment parameters. We also try to link it in the similar way, and we arrive to an equation like this. So if you want to find out what is the velocity with what particle is moving, and if it is a transitionally rough bed, you can use this formula directly. And it's a very, very simple formula with all these parameters what you have with you. You just plug in into that, and you can tell with what velocity the particle will move if it is a transitionally rough bed. Right, and that was the understanding which we got from these all studies here. So it was a complete straight flow was happening, and when the flow was happening, a sediment was dropped there. When the sediment was dropped there inside, this sediment, how it moves, and based on all the observations, we are given one single equation. This equation you can directly use it, so that you will find out if it is a transitionally rough bed. And you should not forget, don't use this for a mobile bed. It is only for a rigid bed. If it is a rigid bed and if the flow is transitionally rough, then use this equation. It will reasonably good value. It will give you, it will tell you the velocity with what the sediment will move. Am I clear? Right. So this is what is the study which we had in a straight flow. Now the interesting part comes. The flow is not disturbed by anything. So we try to understand. If a flow is disturbed, how it is disturbed? Put a pier in between the flow. Very simple. Right? Put a disturbance, just a pier, bridge pier into that. That's all. The whole scenario changes. The whole scenario. Already it is difficult, and it becomes more difficult to understand because of the turbulence, lot of turbulence. I showed you a video. I don't know whether you have seen properly or not, but because of this turbulence, this extra turbulence, when it comes in, this equation, what I have shown you, is null and void. You cannot use this equation because that turbulence is not, external turbulence is not included in this equation. If you don't have any external turbulence, and if the flow was free, and if it was transitionally rough bed, use this equation. If you had an external disturbance, no, never. If you had an external disturbance, what will happen? How to compute that? How to handle that will be my next part of the lecture. Can we break for 30 minutes for this lecture? Coordinators, Dr. Jain or Dr.
Yes, sir.
Sudhanshu?
Yes, sir. Definitely, sir.
Can we have a, I guess it is 2 to 3:30. That's what he told.
Yes, sir. So
can we meet again by 4 o'clock?
yes, sir. No issue. No issue. So now we are keeping one short break of 30 minutes. Then we will start our next third session in continuation at sharp 4 p.m. Okay?
Thank you. Meet you again.
Yes, yes. So dear participants, now there is a break of 30 minutes. We will start sharp at 4 p.m. Okay?
Okay, sir.
Okay.
Okay.
हाँ वे बोलो यार मैं देखा रहा हूँ तो